This lesson is entitled U-Substitution and the Indefinite Integral. Let's consider the antiderivative of 2x plus 3 squared dx. Okay. We want to find the antiderivative based on what we know, which is a power rule. Then we probably would assume this is 2x plus 3 cubed divided by 3 plus c. We're here to tell you, if you do that, you are wrong. And the reason you're wrong, you see, when you find the antiderivative, the nice thing about the antiderivative is you can check to see if it's correct by taking the derivative of the antiderivative. So if we take the derivative of this quantity, which is 3 times 1/3, which is 1 times 2x plus 3 squared, we're not through. We have to take the derivative with the chain rule of 2. We get this, not what we wanted. Okay. Our answer is twice as big as we hoped it would be. In other words, we wanted to take the derivative and get this, but the answer is twice as big. Let's hold on to that thought. We have a remember here, if you integrate and then take the derivative of your answer, you should be back where you started. And here you're not. This is one of the nice things we want to drive home about the antiderivative. Unlike the derivative, you can check your work by taking the derivative of your answer to see if it does indeed give you your original problem. Let's go to the next slide. So we said our answer is twice as large as it should be. So let's just adjust our answer and take half of it was 1/3. So take half of 1/3, which is 1/6. 2x plus 3 cubed plus c. And let's check that. So when we do, we're going to get 3 times 2x plus 3 squared over 6 times the derivative of what's inside, which is a 2. And the 3 times 2 is 6, and the 6 is canceled. It checks. We say here, we leave it to you to check that the answer is correct, but we more or less did that for you, did we not? Let's go to the next. Of course, this is not sound mathematics. Check your answer, alter your answer, make it correct. In addition, this is quite time-consuming, is it not? We have a question. Why does the power rule not work? And our answer is for the same reason the power rule did not work when you took the derivative. If you recall, if you had something like y equals 5x plus 2 to the 7th, we tried taking the derivative and saying, is it 7 times 5x plus 2 to the 6th? And we discovered it was not. And that's where we came up with the chain rule. We found out that the power rule for the derivative only works when you have a letter to a power, but we don't have a letter to a power. We have a quantity to a power, and so we developed the chain rule to take care of that problem. Now, for the same reason, the antiderivative of 2x plus 3 squared dx is not equal to 2x plus 3 cubed over 3, or 1/3, because this is not a letter to a power. This is a quantity to a power. So like with the chain rule, we've got to come up with something that will allow us to work the problem. And since we said it has to be a letter to a power, what we're going to do is just that. Okay. We're going to let the quantity be the letter U. All right. So let's take a problem here, much like the one we just talked about, 2x plus 3 to the 7th. Let's let U be the quantity, which means if we rewrite this problem, it's no longer 2x plus 3 to the 7th dx, it's U to the 7th dx. But we still have a problem. We've got a mixture of x's and u's. We've got a mixture of x's and u's, and we say too many letters. Too many letters. And we need to find a way to get everything in terms of x or du. Now, we already had it in terms of x to start with, and that got us nowhere. So maybe we need to get the dx in terms of u. So this is what we're going to do. If u is 2x plus 3, then du dx is 2, or du is 2 dx, multiplying each side by dx, or dx is equal to 1/2 du if you divide by 2. See, we want dx, so dx is 1/2 du. So what we're going to do is take our this quantity up here, and we are going to put in the place of dx 1/2 du. Like so. And let's put the number in front. Numbers always go in front. Now take the antiderivative, u to the 8th over 8. And now that's 1/16. And let's plug back in. We want to answer in terms of x, not in terms of u, so you've got to get it back. In other words, the question was, what's the antiderivative of this in terms of x? So we have to get it back. So you're not through here. You're not through till you do this. And now, just to restate the problem, this quantity which we were looking for is this, and we're done with that problem. Okay. Check your work always if you have time. And the only time I can think that you wouldn't have time is if you're on a time test or quiz or something of this nature, timed assignment where you are running out of time. Now, we've shown more or less every step here. We'll ease up as we work more examples. Let's take another problem, much like the one we just did. Antiderivative of 15x plus 7 to the 14th power dx. This is my quantity, so I'm going to let u be 15x plus 7. Now, rather than find du dx, I'm just going to write du is 15 dx. In other words, this is called the differential. Du dx is 15 is the derivative. Du equals 15 dx is called the differential. That's small, but we throw that in vocabulary right now because it might be helpful and will be helpful in later dealings in calculus material. So what is it we want? Dx. Well, dx is 1/15 du, is it not? So here we rewrite the problem, and in the place of 15x plus 7, we're going to put u. And in the place of dx 1/15 du, we integrate by adding 1, that makes it a 15. Divide by 15. But we've already got a 15 in the denominator, so 15 times 15 is 225. And so now plug back in, and there is our answer. Again, check it if you need to. Now, let's look at another example. Now, this example is going to show something different, and that's why we're doing it. And we're going to talk quite a bit about this down here, this problem. We talk about them more than you'll be showing in your work, okay? But we're using these to discuss them fully to see if we can head off any questions that may come into your head as you're watching this. So the first thing is, what are you going to let u equal? And that's a problem right now. See, before all we had were antiderivative problems. There's nothing. It either worked or it didn't. But now we have to decide what to let u equal. But generally, if you work enough, you'll figure that out. And we won't try to give you any hard, fast rules right now. So we're going to let u be x squared plus 9. Now, du is 2x dx. Now, look, I let u be x squared plus 9. What did I not let u equal? X dx. So that's the part that's not equal to u. So I've got to isolate x dx. Well, if du is 2x dx, then 1x dx, which is what I want, is 1/2 du. So I come up here, I've rewritten the problem. In the place of this quantity, I'm going to put u. And in the place of x dx, I'm going to put 1/2 du. Now I'll integrate. That goes to 6 divided by 6 makes it a 12. and I plug back in. Now, if you're kind of studying this problem or stopped it for a minute and everything, you may be saying to yourself, you're lucky. You are lucky that you had x and x squared, because I don't think this would have worked if it had not been that duo, x and x squared. We say to you, you're right. This problem was set up the way it is by design. Let's say had the problem read antiderivative x cubed plus 9 to the 5th power, you couldn't use U-substitution. Or had it been just x squared plus 9 to the 5th, you couldn't have used U-substitution. If it had been x cubed plus 9 to the 5th with an x squared here, it could have been done by U-substitution. Now, but this is nothing, not everything can be done by U-substitution. We're just beginning the topic of finding antiderivatives for things that are not just a letter to a power. There's more to the game here than we'll even cover in this section. We'll just say that no, U-substitution does not always work, and you have to find something else. That was the same in Algebra 1. We look here, your teacher in Algebra 1 may have given you this and said factor it, and you did. But if your teacher had given you this and said factor it, it doesn't factor. So you can't factor. You can't factor something that's not factorable, okay? So your teacher had to be careful if they wanted you to factor something to be sure it could be factored. And we have to be sure at this point that we give you something that can be done by U-substitution, since that's the name of the topic here. If you understand this note, then you know what you're doing. If not, you will. It takes a while. Here's a harder problem, much harder problem. Some scares some students when they see this. We're giving you this just to show you, or just to kind of set you back a moment and say, well, he just said it can be done by U-substitution if it can. So let's let U be something. So I'm going to let U be the inverse tangent of x, which is what this is. Well, let's do what we did before. Take du. In other words, the derivative. Well, the derivative of inverse tangent of x is the derivative of x, which is 1 over 1 plus x squared, is it not, with a dx with it? Well, that's exactly what we want. In other words, this thing right here is du. So let's take this problem and put u here. And for this, let's put du. Now we find the antiderivative of this. And then we sub back in. And we're done. And there's your answer. And we know it will check. You might check us out to see if it does. Okay. We did this one not to scare you, but to point out to you 5 things. Relax. Let u equal the quantity and let the step take care of themselves. Okay. If you don't choose the correct u, try something else. Not everything can be done by U-substitution. That's a worry you will have in a later course. In other words, in this course, beginning of calculus, you don't have to worry. U-substitution is the only game in town type thing. But later, when you learn additional techniques, then you're going to have to decide which technique am I going to use. Some things cannot be integrated. That's also a worry you will have in a later course, but not here. You must know your derivative and integral formulas to do this work. Any of this work on antiderivatives requires that you know your derivative and antiderivative formulas. Let's look at example 5. What's different about example 5? Well, what we want to show you here, nothing is really different here, except see this 9 here. We're going to suggest that you pull this 9 out. That's not mandatory. And if you're studying calculus, the U-substitution in a course, and the teacher doesn't do that, that is fine. It just seems to not mandatory, but trust me, I believe it helps, and let me show you why. I'm going to let u be 3x plus 5, 3x to the fifth plus 2, excuse me. Let u be 3x to the fifth plus 2. And I'm going to take the derivative of this thing, and I get 15x to the fourth. Now, if that 9 is there, then what I've got to do is I've got to figure out how to get a 9x to the fourth. What we suggest is you pull that 9 out, and all you need is an x to the fourth dx. What is x to the fourth dx? 1/15 du. Now come up here. Let's just pick up the problem here. We have 9 times. In the place of this, put u, and in the place of x to the fourth dx, put 1/15 du. Add 1 to the exponent, divide by the new exponent, and we've reduced here, and we get this. Now sub back in, and we have our answer. Okay. So there's 5 problems we've done. Each of them now have a different wrinkle. I don't want to say they're getting harder. They just have a different wrinkle to them. But every one is done by the same way. And that's what we're doing these problems for, show you different scenarios, rather than come up here for that first problem, make it this. But also we want to pick up the rhythm of the problem, which is let u be the quantity, find du, isolate what's left over. It's kind of a bang, bang, bang situation. Then come back up here, sub in, do the work with it subbed in, find the antiderivative, which you should now be able to do. And then the last step is put back in for u, it's equal, and you're done. It has a real rhythm to the problem. Let's look at example 6. I'm going to let u be 7 plus the square root of x. What do I'm not letting u equal? Dx over the square root of x. So I let u be 7 plus the square root of x. Du is now the derivative of this. Remember, this is 1/2 power, is 1/2 x to the negative 1/2, which is 1 over x to the 1/2, which is 1 over the square root of x. So we're not showing all the steps. This is what the derivative of this thing is. What do we want? Dx over the square root of x. Dx over the square root of x is 2 du. Okay, so in the place of x over the square root of x, we go put a 2 du and u here, and now we integrate. And we get, when we integrate this thing, we get, we get u to the fifth over 5, which is 2/5, and then sub back in, and we get the correct answer here. Now, one last thing I want to say about this one, in all the other problems, we ended up with like a 1/15 du, a 1/2 du, something like that. And you get the feeling, students often on this problem have a lapse of memory, and even though they get a 2 here, they'll put a 1/2, not a 2. But of course, if you check your work, you'll know and pick that up. Okay. Don't be the person that does that. But if you do that, then go back and correct it. This problem right here, we throw in only to tell you this is what we call, this is strictly a textbook problem. By that I say, I don't think, not that you're going to run into any of these problems in the real world, but this problem is strictly designed to work. It's a peculiar problem. 2x plus 1 times the quantity 3x squared plus 3x to the fifth power. I'm going to let u be this quantity. And what do I not let u equal? 2x plus 1 dx. So let's see if we can get that. We take the derivative, we get 6x. We take the derivative, we get 3. That's all times dx. We factor out a 3. 3 goes into 6 twice, 3 goes into 3 once. And look at what we've got. We've got what, this is what we didn't let u equal. In other words, this thing is equal to 1/3 du. So in the place of this, we put u, and in the place of this and this, we put 1/3 du. That's 1/18 u to the 6. Plus c, and then we sub back in for u, and there is our answer. Okay. This is strictly this problem, you know, like you have something to factor, you can't change anything. It won't factor if you change the 6 to a 7 or whatever, it won't factor. Well, guess what? There's only one thing in this problem that could be changed and it still be done by U-substitution. Now, if I change a couple of things, that's different. But if I just change one thing, if I change that 2 to something other than a 2, it won't work. If I make this a minus, it won't work. If I make this something other than 1, it won't work. If I make this something other than 3, it won't work. If this is something other than x squared, it won't work. If this is other than plus, it won't work. If this is other than 3, it won't work. If this is other than x, it won't work. Okay? So there's only one thing you can change, and this problem is not dependent on it, and we're not going to tell you if you play this over and over again. There's one thing I didn't mention that you could change, and that's the answer to this question we have here. Can you guess what that is? And we're going to leave that for you to ponder. Okay? Now we're actually dropping back to easier problems right now. What we want to show you here is before we've had parentheses, something to a power. Well, you know, you have the formula for the antiderivative of the cosine, and which is a sine, but the antiderivative of the cosine of 5x is not the sine of 5x because it doesn't check, does it? What's the derivative of the sine of 5x? It's 5 cosine of 5x, so it doesn't check. So what we're going to do here is let u be, this is the quantity. In other words, that's the thing that's the problem. We need dx, so we get 1/5. So we put in place of this u, and in place of this 1/5, antiderivative of cosine is a sine, plug back in. We're not going to spend a lot of time on this. The purpose of this problem, this is an easy problem, is it not? We want to emphasize to you that you let u be, in this case, the 5x. Here's another one. Now, this one is, again, you know, we want to make sure you understand the other one. We're not going to spend a lot of time on this one. This is just another one that has, this is much like when we worked before, but show you, in this case, I'm going to pull the -7 out. This I will suggest. We won't make fanfare of this. You don't have to, but we're going to pull right here the -7 out and find the antiderivative of this. We'll let this just be a hitchhiker ride through the problem. We let u be the 1 minus 5x to the 4th, and what's left over, x cubed dx. So if you take the derivative of 1 minus 5x to the 4th, you get minus 20x cubed dx. Okay, we want x cubed dx, so that's minus 1/20th du. So we are going to replace this x cubed dx with minus 1/20th du and the u here. Now, when we this is going to give me 7/20ths. The antiderivative of sine of u, which is a cosine of u. Now, the antiderivative of the sine is minus the cosine, so we have that minus sign there, and then we plug back in. And we make a note here. You must be careful with this example and follow the signs closely, S-I-G-N-S, because you've got negative and then a negative pops back up. Make sure this is a much more difficult problem than some that we've already worked. I would say we've worked 2 and a half difficult ones. The rest of them have been pretty straightforward out of the 9 that we've worked so far. Here is a real hard problem. This one is no kidding about, but we want to show some harder ones. Not that we expect everyone that's reading or listening to this or observing this lesson or whatever is a proper way of expressing it, but we want to make sure if you have this topic pretty much down, we want to make you stretch a bit. So what we're going to do here is let u be the sine of 3x. Derivative of the sine of 3x is the cosine of 3x times 3. We want the cosine of 3x dx, and so That's 1/3 du. So in the place of the cosine of 3x dx, we're going to put 1/3 du. And in the place of the sine of 3x, we're going to put u. And now the antiderivative of secant squared. What has a derivative of secant squared? It's tangent. So we get that. So this thing, just restating the problem, must be 1/3 the tangent of sine of 3x plus c. Is this example difficult? No. Confusing? Yes, we agree. So don't run away from the U-substitution because of this problem, saying to yourself, I can't do U-substitution. This is a more difficult problem, but you want difficult problems. If you're not challenged at all, then what happens when somebody throws you a challenging problem for a grade? You want to be prepared to be able to do anything. Problem 11 is actually drops back to another easy problem. This is an easy problem, just like the cosine of 5x was an easy problem. The integral of e to the 100x is not e to the 100x. Now, we told you something earlier. The only thing whose derivative is e to the x is e to the x, and the only thing whose antiderivative is itself, and that's e to the x. So you know, based on what we've said before, this is not e to the 100x. Now, some people get answers. They will get it and the wrong answer, and then take the derivative and do what we did on that early round, where is we work it wrong and then we go back and adjust it. But let's just go straight forward. U is 100x, so we want dx, so du is 100 dx. Dx is 1 over 100 du. So in the place of, we put u, and in place of dx, we will put 1 over 100 du. The integral of e to the u is e to the u, and then we sub back in. This is an example that you may be able to do in your head. We even hope so. Example 12, we're trying to show you everything possible. What could you let u equal? Let's let u be 3x plus 5. What good is that going to do? Well, let's see. If I let u equal this one, that means I got 1 over u. Excuse me. What's left over? Dx. So let's take the derivative. Du is 3 dx, so dx is 1/3 du. So in the place of u, let's put u. In the place of dx, 1/3 du. Now, what is the integral of 1 over u du? If you've forgotten that, that's ln of absolute value of u plus c. Hey, and we're through. Just sub back in, and there's your answer. Then we give you an alternate answer. You know, 1/3 power. The log of something to the 1/3 power is 1/3 the log. Well, we're doing the reverse. This is the ln to the 1/3 power, which is cube root. So don't worry if you don't see that answer right away. I think this is more the answer that you'll get under most circumstances. Look at example 13. Let's let u be the denominator. Okay, what's left over? X cubed dx. Well, if u is this, what's du? Minus 4x cubed dx. I want dx, x cubed dx. So what's x cubed dx? Minus 1/4 du. So this becomes minus 1/4 1 over u du, which is minus 1/4 ln of u plus c. See, it's again the log, and then you just sub back in and you're done. We're moving quite rapidly here, but this does mean that we don't want to keep you here forever. While us talking about the problem, you can stop it, you can look at it, you can replay it, and that's the beauty of it. But what we're saying is we won't pick up the pace. Now, again, we're trying to emphasize you let u du, and you get what's left over, and then the problem is something you can handle. That's the nice thing. After you get it in terms of u, it's going to be something you can handle on these problems. Another one, what are you going to let u equal? Well, maybe you don't know. We're going to let u be sine of 5x. You say, well, I wouldn't have thought that. Well, we may not either. That's okay not to get it at the right time. What you do is you run into a dead end, something you can't work. So you go back and say, well, maybe I'll make u be the sine of 5x. If u is the sine of 5x, du is the cosine of x dx, which is what's left over. So this is nothing more than 5 to the u du. Now you may, this is one of your more obscure formulas, and this is going to be 5 to the u over 1 over the natural log of the base, which is 5, and then we plug back in. If you're a biology major where you work with, when you're studying things such as cell division, and you're more interested in base 2, often exponential functions base 2, this problem could be of interest to you as well as to others, okay? And then here is a really, this is almost a bonus type problem. Most people who look at this, especially if they've had a lot of calculus where they know other methods, they probably go down the wrong path. This is a tricky problem here, and we don't, the authors of this understand that it is. Maybe some people are looking at this, teachers of calculus think that that's an overstatement, but at any rate, let's look at this problem. Here's the trick to this problem. If you let u be 1 plus x to the 6, you're not going to get anywhere, okay? You're not going to get anywhere because the derivative of x to the 6 is 6x to the 5th, and we need an x squared here. Here's the thing that makes this work. Right x to the 6 is x cubed squared, okay? Now, let u be x cubed, du is 3x squared dx. We need an x squared dx, that's 1/3 du. So this thing becomes here, I'm rewriting it, 1/3 1 plus u squared du. Remember, u is x cubed, so this is u squared. Now the antiderivative of du over 1 plus u squared is the inverse tangent of u, and now you sub back in. Now notice this has to have a lot of things going for it. You have to have this is x cubed, so this has to be x squared to make it work, okay? And this has to be something nice that's up. You could make this say x to the 8th, and if you did, that would be x to the 4th squared. Then you'd have to have probably an x cubed up here. In other words, there are lots of problems that do this. Lots of problems that do this, but you just can't put down anything and expect it to work. So we do alert you, this is a harder problem, but now that we've explained it, is it so hard? It's kind of like once you know the answer to something, then it's not a problem usually, and that's what we're banking on here. Now we want to address one last thing in this lesson before we leave this lesson, and it's we saved it to last, and we hope that everybody will get to this. We almost said at the beginning, please save time to go to the end. I don't know if you've ever thought about it or not, but we integrated the secant squared. It's a tangent. And that's because it derivative of tangent secant squared. But we did not have, when we gave you the list of antiderivative formulas, or your teacher gave you, we assume you've had the antiderivative already. Well, this is a pretty much meaningless lesson. Teacher didn't ask you for the antiderivative of the tangent, the cotangent, or the secant, or the cosecant. None of those. And we ask you, why is there no antiderivative of these? And the why is we couldn't do them. But now, thanks to U-substitution, we can. So let's go to the next slide. Find the integral of the tangent of x. Well, let's write the tangent as sine over cosine. So that means that this thing is this. Let u be the cosine. Du is minus the sine of x dx, okay? We want sine of x dx, so that's going to equal minus du. Sine of x dx is minus du. So in the place of the cosine, we'll put u, and in the place of u, we put minus du, okay? In other words, in place of sine of x dx, we put minus du, and we integrate, and we get minus ln of the absolute value of u, and then we plug back in, and we get this. And we're done, really, except most textbooks do not give the integral. Antiderivative of the tangent is minus ln of cosine. They give it to you as ln of secant. Now, let me explain to you why. Ln of the cosine minus ln of cosine of x is ln of cosine to the -1 power. Remember, when you take, in other words, something to a power, the exponent comes in front of, you can vice versa. So this is to the -1 power. So that's the cosine to the -1 power. That's not inverse cosine. It's cosine to the -1 power, which is 1 over cosine. And 1 over cosine is secant. Okay. And so we write our answer like so. Okay. So we're going to instruct you. You want to learn the antiderivative of the tangent is ln of the secant. Rather than as minus the 1 over the cosine. Okay, so now in like manner we could show the integral of the cotangent is this quantity. We're not going to do that for you. We will give you a hint. You're going to do this. You're going to write the cotangent as cosine over sine and let u be the sine. So try that on your own, if you will. We need that. So we've got 2 of the formulas. And then we don't have the integral of the secant. This one is less obvious than the last one. Here's what we're going to do. We're going to multiply the secant by secant plus tangent over secant plus tangent. You say, can you do that? Of course I can do that. That's 1, is it not? So we can do that. Why would you do that? Well, most of the time, mathematicians, when they're trying to do something, they kind of know what they want, so they kind of build it. So that's this. In other words, they have a right to do this, put this in. Okay. And now if I multiply this out, this is secant squared, secant tangent over secant x plus tangent x dx. I'm going to let u be secant x plus tangent of x. When I take the derivative of secant, I get secant tangent. When I take the derivative of the tangent, I get secant squared. Now this, in other words, dx. Well, this and this are the same thing. Okay. So what I'll do here is I will just simply substitute in for this u. And for this, I'm going to put u. And for this, I'm going to put du. 1 over u du, which is ln of u. So that means, since this u is the secant of x plus, there's your answer. That's the antiderivative of the secant of x. Now, so now if the integral of the secant of x is this, in like manner, the integral of the cosecant of x is equal to this. And what you're going to do here is multiply numerator and denominator by the cosecant of x minus cotangent of x over the cosecant of x minus cotangent of x. Again, if you want to verify that, we leave that for you to do. As I said, these are harder to do, but this is what you want. These are the formulas. So we have 4 new antiderivative formulas, and we're going to, just like before, after we did them in terms of x, we said we want them in terms of u, because it may not always be x, it may be a quantity other in terms of x, and that's the same thing. So let's express them in terms of u, just like we did before. And when I'm talking about this, you had earlier that the integral of e to the x is e to the x plus c. And then when we wrote them in a more useful form, we said, let's do it in terms of u. The antiderivative of e to the u du is e to the u plus c. Same thing is true here. So the antiderivative of the tangent of u is ln of secant. The antiderivative of cotangent of u is ln of sine of u. The antiderivative of secant is ln secant plus tangent. And the antiderivative of the cosecant is ln cosecant minus cotangent. All of these have a plus c added on to them. Now, this is quite a long lesson, but you need to see all of this. It's decided not to break this up into several lessons, parts. Let's go at it the whole way with the understanding that you can stop it if you find yourself lost or tiring or whatever, and you can pick it up later. You look at it as many times. That whole idea is we want you to get this topic down, but hopefully we've gotten across to you. If you know your antiderivative formulas and you know, and you pick U, the proper thing for U, and you go through and U, find du and isolate what's left over, and then when you plug in and get everything in terms of U, it should be something that you recognize from your list of formulas, antiderivative formulas, and you basically have finished the problem. Very wordy, I know that, but hopefully this will be a helpful lesson for you.